This drawing, derived from potential flow theory, shows how the streamlines around a combination of a flat plate and a cylinder would look if fluids did not have viscosity. When a real fluid, water, flows around the same shape, the flow is quite different. Boundary layers, thin layers of fluid in which viscosity affects the flow dynamics, are formed along the surfaces of the object. The behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. This streamline pattern is very nearly what one would predict from inviscid flow theory. Because the Reynolds number is large, influences of viscosity are confined to a narrow region close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress. As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface. Now the airfoil is stalled. A region of recirculating flow is formed over the upper surface of the wing. In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradients, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. The gradient of the velocity normal to the wall, delta u by delta y, times the viscosity mu is the wall skin friction or shear stress tau. The greater the velocity gradient normal to the wall, the greater the shear stress. Upstream, the velocity gradient is fairly large. Downstream, it is much less. This composite photograph compares the two velocity profiles. The smaller gradient downstream indicates the wall shear stress decreases along the plate. The growth of the boundary layer thickness along the plate can be explained by considering the time history of the vorticity within the boundary layer. Stokes' theorem states that the area integral of the vorticity omega, bounded by a closed contour, is equal to the line integral of the velocity around the bounding contour. The circulation gamma is the sum of the vorticity enclosed by the contour. The contour at the upstream station is a unit length along the plate and is more than a boundary layer thickness in height. At the top, the local velocity is parallel to the contour, but in the opposite sense. The components of velocity along the right and left parts of the contour are virtually zero. Because there is no slip, the velocity contribution to the circulation at the surface is in fact zero. Therefore, the circulation is minus the free stream velocity times a unit length. Downstream, the circulation is also equal to minus u0 times a unit length. The total amount of vorticity within each contour is the same. Because there is no vorticity upstream of the plate, and because the circulation per unit length along it is constant, we conclude that all of the vorticity in its length. Upstream, 95% of the total vorticity is contained within this area. Downstream, 95% of the total vorticity is contained within this area. Viscosity acts through the mechanism of molecular diffusion to spread out the vorticity as it is convected downstream. The local boundary layer thickness is a measure of the distance vorticity has diffused away from the plate. We can relate the factors controlling this growth process in the following simplified manner. The diffusion length delta increases as the square root of the product of the kinematic viscosity nu and the time of diffusion t. At a distance L from the leading edge, the diffusion time is proportional to L divided by the free stream velocity u0. We combine so delta over L is proportional to 1 over the square root of the Reynolds number. This relationship is valid only at high Reynolds numbers when delta is small compared to L. Increasing the flow velocity will decrease the boundary layer thickness at any given station along the plate. To see this effect, here is the normal flow.